probability is some kind of measure of the size of the set, how big it is. Okay. All right, let's talk about conditional probability and independence. All right, so you've got a sample space, you have two events, A and B. The conditional probability of event A, given that event B has occurred, is denoted by this, the probability of A, vertical bar B. So the probability of, read this as the probability of A given B. The probability of A given B is the probability of the intersection divided by the probability of B. And of course, this is undefined if B is an impossible event. So, what's the interpretation here? The interpretation is as follows. You conduct this experiment, or your assistant conducts this experiment in a different room. And you want to know what's the likelihood that event A happened. Well, your assistant comes back and tells you that B occurred. Now, that might tell you something about the probability of A. So, before your lab assistant told you this, you had a good estimate of what's the likelihood of A. It's its probability. But your lab assistant just told you that B occurred. Well, that could alter your estimate of the likelihood of A. For example, if A and B are mutually exclusive, and your lab assistant tells you that B occurs, you immediately say, okay, the probability of A is 0. It can't happen. So knowing some partial information about one event might alter your view of the probabilities of other events. That's the whole idea behind conditional probability. If you have this partial information about the experiment, you know that B occurred. Then in some sense, what you know is that you can restrict your sample space to just B. You know that the outcomes outside of B just didn't happen, so you can restrict your sample space to B. So if you restrict your sample space to B, then all of your estimate of all the probabilities of all the events are all going to just take their intersection with B, because anything outside of B you know didn't happen. So the probability of the event A occurring is going to be, well, you take its intersection with B, but then you divide by the probability of B. And the reason to do that is to make B itself the certain event. So, for example, the probability that B occurs given B is 1. Okay? Your lab tells you, the assistant tells you that B occurs, then you know B occurred with certainty. So you have to divide by the probability of B to get that probability equal to 1. Okay, so that's the reason to define it this way. We say that events A and B are independent if the probability of the intersection is equal to the product of the probabilities. So if that's the case, then we say that A and B are independent. And in terms of conditional probabilities, I guess I don't have to waste this anyway. I don't have to write this. An equivalent way of writing it is that the probability of A given B is just the same as the probability of A, and vice versa. The probability of B given A is just the probability of B. So A and B independent, so this is probably another way of seeing what that means, is that somehow A and B don't have anything to do with each other. Knowing that B occurs doesn't really tell you anything about A. It doesn't change your estimate of the likelihood of A. So the probability of A given B is the same as what it was before you knew that B occurred. So a good example is you roll a die twice in succession. Then the probability that the first roll is a 3 is independent from the probability that the second roll is a 5. Those two events are independent. Okay, knowing that one occurred doesn't change your estimate of the likelihood of the other occurring or not. Okay, so one event doesn't give you any information about the other. That's what independent events are.
And you have to know that logic is correct, so there's no real mathematical derivation of, hey, they're independent of one another. You just have to know this event has nothing to do with this event. And so...
Well, yeah. So there are ways to establish independence. Sometimes maybe I just say these two events are independent. Okay? And then you would just immediately translate into either this or these, depending on, and these are mathematically equivalent. Or I might say, okay, if I roll a die twice, and I generally try to say independent. But if you roll a die twice, by physical considerations, you would expect that those two rolls to be independent. So based on your intuition of the real world, you would say, yeah, these events you should model these events as being independent. So that really boils down to modeling the real world as a mathematical, turning it into a mathematical statement. Yeah. All right. So let's do example 1 again. What is the probability that the bit was received, that was interpreted correctly, given that a 0 was received? Okay. So suppose we know that a 0 was received. Now, what's our estimate of the likelihood that it was interpreted correctly? Well, all we have to do is plug in this formula. So we take the probability of the intersection, which we already found, and then divide it by the probability that a 0 is received. So this, you may recall, was 17 30-seconds, and this was 19 30-seconds. So the 30 seconds, the 32 cancels in both places, and you're just left with 17 19s. So notice this is very close to 1. What that means is if a 0 is received, it's highly likely that it was interpreted correctly, if the 0 was received. Okay. If the 0 is not received, well, then that's going to be something else. That's a different story. But given that a 0 is received, it is very likely that it was interpreted correctly. Much more so than if you don't know what was received. All right. We could flip these around if we want. What's the probability if we know that the bit was interpreted correctly? What's our estimate of the prior probability that the bit 0 was received? So here, you can think of what is the probability of a past event, given that we know a future event occurred. It's possible. These timelines don't have to go all the way forward. Well, plug it into the formula. That's the nice thing. You don't have to spend too much time interpreting this. Just plug it into the formula, and that's 17 30-seconds divided by, well, we got that as 28 30-seconds. So that's 17 28s. Okay. So if you know the bit was received correct, if you know the bit was interpreted correctly, here is your estimate of the likelihood that a 0 is received if you didn't know what was actually received. You just knew that it was interpreted correctly. All right. Are C and R not independent? No, they are not independent. So what's one way of seeing that? Right here, we can see it this way. So the probability of getting a C was 7/8. Or if you like, this is 14/16. But the probability of getting a C, given that a 0 is received, was 17/19. And these two are not equal. In fact, this one is slightly bigger, right? So if you know a 0 is received, that increases your estimate of the likelihood of it being interpreted correctly by just a little bit, not a whole lot. Okay, so they're definitely not independent. How about these? Are perm and G3 independent? Okay. So perm was 2/3. G3 was 1/2. Let's use the first rule for independence and say, let's take the intersection. What's the intersection here? 5. It's just 5, which is 1/6. But if you take the product of these two, you get 1/2 times 2/3. That's 1/3. That's not equal to 1/6, which is the probability of intersection. So here, the product of the probabilities is not equal to the probability of intersection. So these events are dependent. They are not independent. What this says in particular, that is, if you know, well, let's suppose you know that something greater than 3 was rolled, then that actually decreases your estimate of the likelihood that it's prime. Okay, than if you didn't know anything. All right. So if they're not independent, if they're dependent, there are two possible ways of considering it. Maybe the probability of the intersection is bigger than the product. If that's the case, then we say that A and B are positively correlated. That means that A and B more likely occur together. If the probability of A intersect B is less than the product, then we say A and B are negatively correlated. That means they're closer to being mutually exclusive. They tend not to occur together. Here's a good picture. Here's A. It's this shaded region here. Okay. Here's B. It's this shaded region here. It's the red region. That's B. Okay. In this case, the probabilities are independent. Because if this is, say, if this is P, so this width is P, that's the probability of A, because it's taking up a P fraction of the whole square. So let's call this thing Q. That's the probability of B. That's taking up this fraction, a Q fraction of the whole square. Well, what's the probability? What's the size of this rectangle? It's P by Q. So it's P times Q. That's the probability of the intersection. So in this picture, it looks like A and B are independent. And I've kind of drawn it that way. A only depends on the horizontal position, and B only depends on the other way around. Sorry. No, I got that right. A only depends on the horizontal position. Where you are horizontally determines whether or not you're an A. And B only depends on where you are vertically. So maybe those are independent, and in this case they are. Now, if A and B are positively correlated, then the picture might look more like that. Here's A and here's B, and they have an intersection that's bigger than what you would get if you just multiplied the probabilities together. So these are positively correlated A and B. And negatively correlated B would be you tilt these lines in the opposite direction. Now they have a much smaller intersection than what they would have if they were independent.
So, sir, another way to look at it might be that you can, if the area of intersection between the two are greater than than that which exists without one another, then they're positively correlated. And if the intersection between the two is smaller or contains less of the outcomes, then it's negatively correlated than the actual two events occurring on their own.
Yeah, well, yeah, you gotta be a little bit careful about here. It's because you just probably it's just I don't know, the P of A times P of E. I don't know what that means in terms of area. I mean, written like this, it's this rectangle for sure. Okay, but you would have to if A and B could be weirdly shaped. Okay, they don't have to be like this. If you squeeze them in like that, then it's going to be the area of the rectangle. But that's, I don't know. I'm not good at this. All right. So, some quick, this is kind of a digression. If you have a data set, so you run an experiment, and let's say the outcomes are actual real numbers that you get. Like you measure the acidity of a certain solution, or you measure the number of inches of rainfall in a given hour, or, you count the number of jelly beans in your hand, and you do this several times, or something like that. You get some number out of it, and you get a set of numbers because you run the experiment several times, and each time you run it, you get a real number, and you collect those real numbers into an n tuple for n runs, and we call that a data set. Well, some useful single numbers that you get out of that are, one is called the mean, or the average. And what you get is you add all the numbers together, and then you divide by the number of data points. So this gives you the average value of your data. It's kind of a point sort of right in the middle of your data set. Okay. What are you getting on average? So maybe n is 300 million is the population of the United States, and the x's are personal income. This gives you the average income of an American citizen. So that would be the average income. That's how you get the average personal income of somebody living in the United States. And if the data set, if we call this thing x, that whole tuple is x, then we usually write x bar to denote the mean or the average of a data set like this. All right. So this gives you an idea of sort of where the center of your data is. There are other ways of doing that, like you could take the median, which is another way of getting somewhere close to the center. Median and average have different properties. We're going to stick with average. We're not going to talk about medians. But the variance is sort of a measure of the dispersion or the variation in your data. How are your points widely dispersed, or are they all clumped together in one place? So are they mostly equal to each other, or are they widely scattered? And the variance gives you a measure of that. What you do is you take each number, subtract it from the mean, subtract it from the average. So this will tell you positively or negatively how far away you are from the mean for each data point. How far each data point is from the mean, but you square it. What does squaring do?
It takes out the mean.
Yeah, squaring makes it positive. So no matter which side of the mean you're on, you're going to get a positive contribution, and that contribution is going to increase the further away you get from the mean. So the further we are from the mean, the larger these terms are going to be. Well, essentially, we just add up all these terms and divide by the number of points. Well, for technical reasons, you divide by the number of points minus 1. But if n is large, you could divide by n and you wouldn't get a significantly different number. Okay. This is called the sample variance. This is called the sample mean. This is called the sample variance. Usually denoted by s squared. The units of s squared are in the square of the units of the data points themselves. So, for example, if this is inches of rainfall, so these x values are in units of inches or centimeters, let's say inches, then the variance is going to be in units of square inches. So it's a little strange. So we want a measure of the dispersion back in the same units that we started with. And so instead of taking the variance, we take what's called the standard deviation, which is just the square root of the variance. So this gives a measure. This gives a good measure of the dispersion, and it's in the same units as the data points in the sample. All right, so let's take an example of this. Two extreme examples. Here's one data set. Here are the values you get from 5 runs of the experiment. Here's another data set. We run it 10 times, and we get 6s each time. All right, so what's the mean for set 1? Add them all up, divide by 5, and we see that the mean is 6. That's right in the middle in this case. Here, you add these up, which is just taking 6 and multiplying it by 10, but then you divide by 10 because you divide by the number, and you just wind up with 6. So if all the data points are equal, the mean is certainly going to be equal. All right, so what's the variance? Well, which variance is going to be bigger? Set 1 or set 2? Set 1 is going to be bigger, right? Set 2, what do you think the variance is for set 2? 0, right. Every one of these is equal to the mean, so you're just adding up zeros. You subtract the mean and square it. So for set 1, subtract each data point from the mean, which we got as being 6. 2 minus 6 quantity squared, 4 minus 6 quantity squared. Add them all up, divide by the number of points minus 1, and we get 10. So the sample variance on this side is 10. Sample variance on this side is 0 because we're just adding up zeros. The standard deviation then on the first side, so we call the sample variance S1 squared, so the standard deviation is just called S1. The square root of 10, which is about 3.16, and the square root of 0 is 0, so we just get 0 for the standard deviation. Okay. Here's another way of looking at the data sets. Here is the first data set. You have bars for each data point. And if 2 data points are equal, you just stack the bars on top of each other, as we do over here, where they're all equal to 6. So we get this big bar here. So this is highly dispersed. This is one big spike, right at 6. All right. So we won't really be dealing with the sample mean and sample variance anymore. But we're going to be dealing with what we call the true mean and the true variance when we do random variables. The reason to talk about this is that if you don't know what the mean and variance are, if you don't know what the true mean and true variance are, all you can do is take some random sample, run the experiment some number of times and take a random sample. The sample mean and sample variance give you your best estimate of what the true mean and true variance are. So census takers do this all the time. You want to compute the mean household income in the United States. You can't survey every single house. Well, I don't know, maybe you can. Maybe give another example. You take a poll, okay, and you want to find out household incomes, and you call up a random sample of houses and ask what their income is. That's going to give you a mean for your sample, okay? That mean is your best estimate of what the actual true mean household income is for the whole United States. Now, the bigger your sample, the more likely you are that your sample mean is going to equal the true mean. So bigger samples are better than smaller samples. Your sample variance is also your best estimate of what the true variance is. Okay. So we haven't talked about the true variance yet. That's coming up in the next. All right. So random variables. So we're back to math, away from statistics. All right. So you have a sample space S, and here's what now we're going to do. For every outcome in S, we are going to associate some real number. Not necessarily probability now. This number may not be in the range 0 to 1, but it's just some arbitrary number that we associate with that outcome. So, for example, if the experiment is, I reach my hand into a jar of jelly beans and I pull out bunch of jelly beans. That trial of the experiment, the number associated with it might be the number of jelly beans I actually pulled out. Okay, or if I'm measuring the amount of rainfall in a given day, so the outcome is the particular day I choose. And there may be 365 outcomes if I do this every day for a year. There would be 365 outcomes. The actual amount of rainfall I get on any given day is a number I associate with that outcome. So a random variable is just some function that associates some number with every outcome in a sample space. The probability measure also, associates a number with each outcome, its probability. So actually, the probability is an example of a random variable. It's a special random variable. But now, a random variable could be lots of different things besides probability. There are two types of random variables, depending on what the space of possible values there could be. We call them either discrete or continuous. A discrete random variable means that the outcomes, there are only a finite possible set of values that the random variable can take on. Or possibly just a countable set, but it's a discrete set. Whereas a continuous random variable, the value of the random variable could be any value in some continuum. Okay, there's no limit. It's an uncountable continuum. So let's do some examples. So here's a random variable, the number of eggs in a robin's nest. So you go out and you pick a random tree, and you climb the tree, and you look in the robin's nest in that tree, and you count the eggs. That tells you the value of that random variable. Okay. So in this case, the outcomes are the robin's nests themselves. And each outcome, so you might pick a robin's nest at random. Each outcome is the number of eggs in that nest. So it's a number associated with that outcome. What do you think? Is this a discrete random variable or continuous? It's discrete because the number of eggs has to be an integer. We don't consider fractional numbers of eggs. It has to be an integer. Integers form a discrete set. Inches of rainfall in a given day. So the outcome is a particular day, which you might choose at random, and you measure the inches of rainfall during that day. Discrete or continuous? Yeah, this should really be continuous. I mean, you can argue that because rain is made out of molecules, which are discrete entities, then this really should be discrete, but that's really pushing it. I mean, for practical purposes, this is a continuous random variable. Yeah.
If you measured rainfall like to the nearest tenth of an inch,
yeah,
would that make it a discrete set?
Mm-hmm. Yeah, if you round it off to the nearest tenth of an inch, that would make it discrete.
Okay.
Yeah, absolutely. It is the criterion is consider the set of possible values you will allow the variable to take on, and if it's just every tenth of an inch, that's a discrete set of notches.
Okay.
All right. GPA of students in the university. So the sample space is the student population of the university, and the outcomes are students. And for every outcome, for every student, there's a GPA, which is some value from 1 to 4. What do you think? Discrete or continuous?
I'd say continuous
That's based off of the last question.
Yeah, I don't know. I think you could actually probably argue either way on this. It might be easier to treat it as continuous if you have a large sample of many students who have taken many, many classes. So it's not worth trying to actually find enumerate all the possible discrete values that a GPA can take on. It might be easier in the analysis just to assume it's a continuous random variable. But if you have students only taking just a couple, maybe 2 classes per student, and the possible values of the GPA are 1, 2, 3, 0 through 4, then maybe it's worth making it discrete then. But I think if with a large sample of students and each student takes lots and lots of classes, it's probably easier to model this as a continuous variable. All right. W, number of defective network interfaces in a shipment. Discrete because it's a whole number. Okay. So what are the outcomes here? The shipments. Right. So the outcomes are the shipments. It's the thing that you associate the number to. So it's not so a shipment is an outcome, and you count the number of defective interface cards in the shipment. That's a continuous. So we'll say that X and W are definitely discrete, and Y and Z are arguably continuous. All right, questions on random variables? So we have to treat discrete and continuous random variables slightly differently, because what we're going to do now is associate important numbers with each kind of random variable. And the first type of random variable will deal with our discrete random variables. So a probability function what this does is assigns probabilities to the values that a particular random variable can take on. So here, it's a little bit confusing. This is a capital X. We denote that's going to be the random variable, capital X. And it'll take on some set of values, some discrete set of values. Each value we'll call little x. So that's a lowercase x. See the difference? Okay. So the random variable is taking outcomes. Each outcome has a probability. So we can ask, what's the probability that the random variable equals a particular value? Well, this inside here is really an event. You look at all the outcomes where that random variable gives you this particular value x. It's the probability of that event. So we'll let p of x be the probability that the random variable equals some particular value. We call that the probability function. So, as usual, this is the probability of this particular event. So you could get it by, say, adding up all the probabilities of the outcome in that event, outcomes of that event. So here, we're adding up over all outcomes A in the sample space, such that x applied to A is equal to little x. So capital X applied to A is equal to little x. So the random variable value at A is equal to this particular little x we're talking about. Add up those probabilities. That gives you the probability of that event. So the probability that the sample, that the random variable equals x. Okay, so that's just the event. So we have some properties here. Suppose B is the set of all possible values of x. Then, well, these are probabilities, so they've got to be between 0 and 1 for every value x and b. These are the value restrictions. And the normality condition is that if you add up all the possible values the random variable can take on, if you add up all their probabilities, it has to equal 1. Because every event, every outcome in the sample space is going to give you one of these possible values. And it's never going to give you 2. So we're adding up disjoint events that whose union is the entire sample space. So we add up all the possible values that the random variable can take on, add up their probabilities. That has to be certainty. if you like, you could think of V now as a sample space. And the P are just, these P's are just the probability of each outcome. And the outcomes are just the values now. That's another way of looking at it. All right, so we'll do some examples in a second. The cumulative distribution function for a random variable x, we call that f. This is the probability that x is less than or equal to a particular value. So this is another function of a real number x. It's the probability of this event, that the value of the random variable is less than or equal to, say, 10, okay? Or some any x. And the way you can get that is you can sum over all the possible values less than or equal to x, sum their probabilities. Thinking now the y's is now being the outcomes. So this is the sum over all possible values less than or equal to x, the probability of getting that value, getting y. And that gives you the total probability that you're less than or equal to x. All right. The expected value of a discrete random variable x is, you take all the possible values of the random variable, you take x times its probability, and then you add these up. That's called the expected value of x. This is also called the true mean, or the true average value of x. Yeah.
Is that you sum the probability of each of the separate values, or the probability that it's just within that range of values?
You do this for each of the individual separate values. So this is for a discrete random variable. When we get to continuous random variables, we're going to have to do something different, like what you said. You take ranges instead of just actual values. Okay. But the point is, this is a single number. Let's see. How am I doing on time? Couple minutes. Okay. Actually, let me just do one quick example on the board, and then we'll take our second break. So, S is a six-sided die. So this is going to be 1 through 6. And now the random variable is just going to be the same number as the outcome. It's just going to be the number showing. So let's let n equal the number showing. Okay. So v, the set of possible values of n, is going to be 1 through 6. Okay. Now each one of these, if the die is now balanced or fair, that means what? Remember? Yeah, uniform probability distribution. So every outcome occurs with probability 1/6. Let's compute the expected value of n. Well, we're summing over all the possible values in V, and that's just 1 through 6. So we're summing for little x equaling 1 to 6 of x times its probability, the probability of getting x. What's the probability of getting x? 1/6. Right, so this is the sum of x times 1/6. X equals 1 to 6. Okay. So if I write this out longhand, I'm going to have 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. Well, instead of doing it this, what a shorter way might have just been to factor out the 1/6 out of the entire sum. So that's 1/6, and I get 1 plus 2 plus 3 plus 4 plus 6. What back? 21. The 21? So this is 21 over 6, which is 7/2, 3.5. So the expected value of a die roll is 3.5. Okay, that's called the expected value. It's the average value. If you roll the die 1,000,000 times and you added up the values of all the rolls and divided by 1,000,000, you're most likely going to get something very, very close to this. Okay. So the expectation is essentially the average value of the random variable, okay, which you can estimate empirically by running the experiment many, many times, adding up all the results, and dividing by the number of trials. Okay, so that's the expected value of X. Questions on that? This is really the true average that you get closer and closer to as you take bigger and bigger sample averages. All right, good. Let's take another 8 minutes. Come by when the hand's on the 8.
It's just saying like it could be anything. Right now we're not trying to put anything solid to it. We're just right now like that was one of them.
So like the random bit, like you haven't. This is stupid, but you have not looked at the robin's nest.
Yeah, you don't have any control over it.
Right. So you don't know how many eggs are in the robin's nest.
You're just gonna look
You're
at
saying.
get what you get.
Right. So you haven't looked at it. So you're just saying, oh, that robin's nest is going to have like X number of eggs, and we'll say that X is 18.
You're saying the robin nest has X number of eggs. I don't know X is class.
Right. But we haven't looked at it.
So that's
We haven't looked at it.
But we will look at that.
So like, but right now, what the
Yeah. It's okay you say random because you have no idea what's in there without looking. Right? Like it could be there could be 1 million eggs in that nest because that's why you're just saying random because there's no rhyme or reason to why when you look into it you'll be eggs.
Okay.
He's got it. Yeah, he's got it. So worried about you.
It's my one, you know, it's been a month.
That makes sense now. So like this is so we like assign a random number.
I mean, as far as I know, it's still like
This is the
like
probability
expectable life, isn't it?
that
That's why I use it as a joke because
when we actually
they're
look
required
at
to keep
this,
it on me. No one ever has one. So.
that if the random number was 2, that there actually would be 2 eggs.
What if it's still like if you say the two of them, like you're saying like okay, I think it's probably 2, 3, or 4 eggs.
I just threw mine away last night.
What's that?
That's
Did you mind away last night?
I like
randomly.
So mine was like from like 2009.
Yeah, so
Apparently they stopped printing them after that.
Really?
You had to like choose. It was the weirdest thing. Like they were a special item, but you couldn't get them anywhere.
What?
They don't do it here. Everywhere I've been. It's just like a book for each poster. Yeah, it's still in Carson. You have to have it.
okay, information about
Yeah.
In Alaska, it's a little bit more sense.
It's open to some.
Little X is the actual number.
Little X is kind of like, you know that there's not different, like,
And it has 6 layers. It
Right.
has different temperature ranges, which is different
it's
layers.
like you kind of already have an idea, like, okay, this will
And
usually
like,
have
depending
2,
on what
3,
you're
or
doing,
4.
if you're going to the range,
Right, so that's your little X.
You didn't have all your layers.
Your big X is now a probability. Your big X is when you look at this.
Yeah, and so that was probably all it was good for that.
You look at that, probability of actually
You figure out pretty quick what you really need to wear.
because this
Before
one,
they had
And now they're talking
Oh,
about
yeah.
some companies
I
might
thought
buy
that was little or big X.
big X is what you actually randomly
It's about it.
It's like oxymoron.
Let me tell you.
Well, because like there's no mathematical function of wild. You can't just look at this and get rid of it.
No, yeah.
That's why it's
Well played.
Right.
Well played.
But when you look at it, you'll see the actions.
Is
That's
that
your
little
big
X?
X. That's big X.
That's big X?
Well,
Little X is you still have is like okay, I have 50 nets, and I'm gonna say that within the nets, probably the only
well, if you see that,
possible
if that was part
It's
of
in my
his,
contract. You know.
number of
that was
X
his contract, he was actually obligated.
Okay.
I don't know, we're big.
Fiduciary, that's the word I'm looking for. Because that guy's a fiduciary.
and all that is telling me is that
I don't know, that would be the other.
the probability
But you like, find that it's like, no one's gonna buy,
Why don't our contract say that?
because we're not fiduciaries. We're not fiduciaries.
the probability of you finding
Our contract's always say one.
And that's the guess. Like, oh, Robin is going to have him looking at
Oh,
probably.
that's what I was gonna say, but I don't know. Hostess and
little
That
X
was, that was one of the other amazing things was like, you people leaders, like, they asked,
big X is what you're actually
See,
that's just telling me that
it's a probability
the
that
probability of you
a big
getting
X.
2 is the same as equal to
Right.
yeah, I don't really think about
the
the
same as the
Someone's
probability
gonna buy this, and then we'll still look for that.
actually
And
is
it's
the same as like say
it's like, really, you think so?
you just happen to know that the probability of equaling the 2 is 1/5.
I think Hostess,
So
you make that healthy food when you were, you know.
looking in there and seeing 2 should equal
How many people are actually following that? That's the.
That's true, but like,
Most of America's still fat.
like kind of like
well, the 60,
when you were showing the example with the signification, right? Where like one had 16 out of 30,
Maybe
one out of 13, one out of 15.
And they made like 12 out of every
with those apple pies, right?
So
There's nothing like, yeah, you're cherry pie. Did you have a house cherry pie?
case 1.
There's always not.
Yeah, I don't remember.
There was a common, but
No,
I avoided it.
Is
we had one, and again, it's the 1634. Did you have a chip
say
apple?
you like that wasn't a box, right?
Remember, like,
My cherry chip was
But you all know the
Q part.
possibility that 80% of the food is actually 16 out of 30.
Oh, okay. Me and,
So
but
that
me and my
should
friend, like,
equal
for my cherry jump,
opening
you know, I had the cherry pie, and of course, it's cherry jump. I said, so, this your cherry jump? Yeah. And run on your cargo pocket every time, so you have, like, goofy cherry, like, every one of them. It was lovely.
Where's
Jesse's, yeah. Something on his pocket.
pretty young.
Hurry up. Cut that thing off.
It was very captivating. So.
All right. Okay, let's get started.
There you go.
All right. So we just did the expected value, which is the same as the average. So next up is the variance. So the variance of a random variable, again, is how sort of a measure of how widely dispersed the values can be of a random variable. So to do that properly, just a couple basic quick definitions here. There's the constant random variable that is always equal to the same number for all the outcomes in the sample space. We'll call that the constant random variable. And we'll just label that with the value C for the constant. So C here is a real number. You can manipulate random variables just like you manipulate numbers. And the point is, and you'll get new random variables out of that. The point is, the way you do that is, if you have a new random variable, if you have x and y are random variables, then you can make a new random variable, say x plus y. That's a new random variable. And the point is, x plus y maps each outcome to the sum of what x maps it to and what y maps it to. So you just evaluate the sum of two random variables at each outcome and take the sum. So you're just adding random variables together like you add numbers together. Okay, you're adding their outputs. Essentially, that's what you're doing. Okay, same with multiplication. Easy enough. And all the other functions you can think of applying to numbers, you can also apply to random variables. You just apply them to the outputs of the random variable. All right. And then you get another random variable that way. All right, that's enough to define the variance by this god-awful thing. If x here is a random variable, v of x is the following. First, you take the expected value of x. That's e of x. That's a number. That's a constant number. You then subtract it from the value of x itself. So for each outcome, this is going to give you a different number. You subtract this same number, the average, from it. Take that whole thing and square it. That's a new random variable. You then take its expected value. So the idea is that this piece in here is a random variable that is giving how far is the actual number deviating from the mean. That can deviate in either direction. So we want to square it so that we always get a positive contribution. So this is just like with the sample variant. We square it, and that will give you a positive contribution, and it's going to be bigger the farther x gets away from its actual mean. You then take the expected value of that thing. Okay, that's going to give you sort of the average square difference of a random variable from its mean. That we call the variance of the random variable. It's just like the sample variance. In fact, the sample variance gives you your best estimate of what the true variance is. If you run the experiment 100 times and record the value of the random variable each time, that gives you a data set. You then plug into the formula for the sample variance, that gives you a good estimate. Provided you have a large sample, that gives you a good estimate for what the actual variance is. There's a simpler way of expressing this. It turns out you can manipulate this a little bit and take the square of the random variable, so x times itself. Take that expected value and then subtract off the mean of the random variable squared. So this is a number, it's squared. This is a random variable. You square it to get a new random variable, and then take its expected value. Subtract those two things together, you get the same value, get their variance. We also denote this variance by lowercase sigma, sigma squared. Excuse me. This is a single number associated with a random variable. It's always positive or 0. And the only time it's 0 is if the random variable is constant. It gives you the same number every time. Well, just like with the sample variance, this is in the units of the variance are in the square of the units of the random variable. So if x is in inches, v of x will be in square inches. So to get it back into inches, we'll take the square root of the variance. We call that sigma. That's called the standard deviation, just as before. All right, so let's do an example. You toss a fair coin 3 times. Got to be 3? Okay, yeah. Oh, all right. Yeah, 3 is good. 4 is too complicated. 2 doesn't work our brains enough. So it's got to be 3. So here's the random variable. So you toss a fair coin. So fair means what? Fair means equal probability of heads and tails, which is then what for each? 1/2. Okay, so heads, probability of heads is 1/2, probability of tails is 1/2. Now you flip it 3 times. What's the sample space? It's going to be all combinations of the first flip result and the second flip result and the third flip result. How many combinations are there? There's 2 possibilities for the first one, and for each of these, there's 2 for the second. So that's 4 for the first 2. And for each of those 4, there's 2 for the third. So that gives 8. Good. Okay. So the sample space has size 8. And since it's a fair coin and these flips are all independent, every combination is equally likely. So every outcome is going to be with probability 1/8. So here's the random variable we're interested in. The number of heads you get with 3 flips. Okay. So here's the sample space. We can list it this way. For example, heads, 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 tails, heads, tails, heads, heads, tails, tails, and so forth. First flip, second flip, third flip. Okay, so you think of the flips as being labeled. So you definitely keep track of which flip is which. All right. So if you apply this random variable, say, to the first outcome, it's 3, because that's 3 heads. Apply it to the next one, you get 2 heads and a tail, and so forth. Okay. So what are the possible values of x? 3, 2, 1, or 0. Okay, so there are 4 possible values: 0, 1, 2, or 3. What's p of 0? 1/8. Why is it 1/8?
Because only once when you receive all tails.
Yeah.
It's in the possibility.
Okay, good. So the event that you get 0 heads only corresponds to 1 outcome. And that's tails, 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 which occurs with probability 1/8. So p of 0 is probability of that event, which is 1/8. What's p of 1? So how many ways can you get 1 head and the other 2 are tails? 3, right? Because it could be the first one, it could be the second one, it could be the third one, and the other 2 are tails. So that's going to be, it's going to be these 3 outcomes, and so each one is probability 1/8, so this is going to be 3/8. Okay. Nice uniform distribution. Okay. And so forth, p of 2 and p of 3. So what's f of 0? This is the probability, this is the cumulative function. This is the probability that you get at most 0 heads. Well, how do you get at most 0 heads?
If you have 0.
Yeah, if you get 0, if you get exactly 0, that's the only way you can get at most 0 heads. So this is the same as this, which is 1/8. But what's F1? This is the probability of getting at most one head.
0 or 1.
0 or 1.
Yeah, so it's going to be, you can do this by getting 0 heads or 1 head. So you add those two together. They're, of course, mutually exclusive. So add them together, and you get 4/8 or 1 head. All right, so here's a plot of the probability function and the cumulative function. So for the 4 possible values of the random variable, here the solid bar gives you the probability of getting that value exactly. So the probability of 0 is 1/8, which is about 1.25. Sorry, 0.125. Probability of getting 1 is 3/8. Probability of getting 2 heads is also 3/8, because notice there are 3 ways of doing that, because it's where the tail comes. It's the first one, second one, or third one. So it's also 3/8. And then the only thing left is getting all heads, and that's 1/8. Okay. So that's the probability distribution. That's the probability function. The cumulative function is everything less than or equal to the current value. So for the smallest value, it's just equal to the probability. For the next value, it's equal to the previous value plus the new probability. For the next value, it's equal to the previous value plus the new probability. And finally, for the last value, it's equal to all the probabilities added up. So, in fact, the cumulative function is always ascending. It never decreases. And its level is equal to the sum of the heights of all the bars. If you stack the bars on top of each other at the current point and to the left, you get, then you get the cumulative function that way. Okay? Questions? All right, so that's a plot of what's going on. What's the expected number of heads? That's leaving a message. What's the expected number of heads? So we sum over all the possible values. So it's 1.5. Very good. All right. Got that one right?
Yeah, team.
You sum over the possible values. So here's how you do it if you didn't see that yet. 0 through 3, those are the possible values. Take the value itself. So x is going to be 0, 1, 2, 3. Multiply it by its probability. So that's 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. And that would be 1.5. Very good. What's the variance? Well, to get the variance, we can use, say, this formula. Well, if I unpack this thing, this expected value, what I'm doing is I'm taking the expected value, I'm summing over all these values times their probabilities. That's how you get an expected value. So these values are x is 0 through 3, and I subtract this. Well, what's this?
1.6.
It's 1.5. So this, I'm always subtracting the same number each time. And I square that, multiply it by the probability. So doing that all in detail, I get 0 minus 1.5 squared times that probability 1/8. 1 minus 1.5 squared times 3/8, and so forth. And if you do all of that, you get 3/4. Exactly. So simplify all that, you get 3/4. So the standard deviation is the square root of 3/4, which is about 0.866, approximately. All right. Okay. So questions on computing those things. How is this for people? What's your comfort level on this? Is it this way, or that way? That way. All right, that way. Okay, at least I'm getting everything. All right.
It's all coming to me now.
So let's actually apply this to a practical situation. 3 coin toss game. You pay $5 to play this game. You're at a state fair or carnival, and it's not a very imaginative game, but you pay $5 to play this game, and here's what the payoff is. For every head that appears, you'll get $3 back. Is it worth your while to play this game? That's the question we want to answer. No.
The coin calling off
They're still in the quarters.
Yeah, the coin may probably not be fair, but let's assume that the coin, you know that the coin is fair. Maybe the guy allows you to actually just use your own coin.
Then definitely my coin wouldn't be fair.
Yeah, then definitely.
It's fair for me.
So the way to answer this question is, how much money do you win or lose on average? Okay, so if you do this many times, you're likely to lose the average amount likely to win or lose the average amount times the number of times you play it. So, all right. So here's the random variable. X will be your net winnings. So it's your winnings minus the overhead you pay up front, $5. We want to find the expected value of X. So we've got 4 possible outcomes, 0 through 3, number of heads. Here is your winnings for each. So $5, if you don't get any heads, you lose $5, so it's minus. And then you increment by $3 until you get it. So it's $4 if you get all 4 heads. Okay. Here are the probabilities. We've already done them. And so if we just multiply each entry X times its probability, we get this column over here. Now the expected value is just the sum of the entries in this column, which turns out to be minus 50 cents. So you can expect to lose, on average, 50 cents every time you play this game. So don't play. All right. That's it for the general discussion of discrete random variables. Now we need to talk about continuous random variables. To do that, we need a quick refresher on definite intervals. And there's going to be more on definite intervals later when we do waves. But to understand just the basics of the distribution functions for continuous random variables, we need to talk about intervals. So let f of x be a real value function, and let a and b be real numbers, and say that a is less than or equal to b. Then the definite integral of f from a to b we denote like this. It's this old-timey sum thing. That's actually an old-timey s. And the limits, we put a on the bottom and b on the top, and we write f of x dx. This is the area of the region between the curves y equals f of x and the x-axis. Those are the vertical borders, and the horizontal. Those are the horizontal borders, and the vertical borders are the vertical lines of x equals a and x equals b. So, in pictures, you've probably seen this before. There's A, there's B. Function looks like that. All these vertical lines, it's that area. So this is y is f of x. That area is the integral from a to b of f of x. Okay. So one way of getting an integral for for functions that are reasonably well behaved is to think of this as a limit of a sum. So how would you, if you wanted to estimate the area, what you could do is you could chop up the area into little rectangles where the width of the rectangle is the same width, say delta x. And the height of the rectangle is the value of the function at that point. Say maybe let's say the left border of the rectangle. Like that. Okay. And there might be some overspill. And if you sum up those areas, what you're going to get is you're going to get the sum. Well, let's write it this way. Instead of writing this as a sum, you could write it as f of a times delta x plus f of a plus delta x times delta x. That's the area, that's the height times width of the first rectangle, height times width of the second one, and so on. You can write this then as a sum of f of a plus k delta x. Okay, and then k runs from 0 to whatever, however many k's you need to get to b. Well, to get the actual area, what you can do is make these rectangles very, very thin. And the thinner you make them, the closer to the area you're going to get. So the integral is going to be the limit as delta x approaches 0 of this sum. And just like with differential calculus, when you take the limit of delta x getting to 0, it turns into dx. So this dx has the same role as it did in the differential case. This is like an infinitesimal width, an infinitesimal change in x. And for each infinitesimal change in x, you're multiplying it by the value of the function. And instead of taking a discrete sum in the limit, you take this continuous sum. So you think of an integral as sort of being a continuous version of a sum, where you're summing up all these little tiny thin strips across the region from A to B. Okay. So when you go from a discrete random variable to a continuous random variable, generally the formulas are going to be similar, except that sums are going to turn into integrals. That's really the big difference. Okay, because we want a continuous version of a sum. All right. The other thing, just that last statement here, is if x goes below the axis, you count anything below the x-axis, you count this negatively. So this subtracts from the net sum. So these are sign quantities. These could be positive or negative. Okay. All right. But in our case, actually, it won't fall below the x-axis. Okay, so here we go.